Hi everyone, today we're going to talk about average atomic mass. And when we take a look at average atomic mass, we're taking the average atomic mass based on all of the isotopes of a certain element. And so remember, isotopes have a different number of neutrons, and so that makes the atomic mass different. So we can take a look, and we'll see later on in the video. We're going to talk about chlorine 35 is one isotope, and then the other naturally occurring isotope of chlorine is chlorine 37. And so these are isotopes because their mass number is different, and so that makes the number of neutrons different. Because remember, they'll still have 17 protons each. But since this is chlorine 35 and this is chlorine 37, chlorine 35 has 18 neutrons because of 17 plus 18 equals 35. And then chlorine 37 will have 20 neutrons. And so what happens is on the periodic table, when you see the average atomic mass, it is actually the average, a weighted average of all these. So when I'm talking about weighted average, let's take a look at an example. So maybe we had a few test scores, and a student scored 100 on the first test. Good job. A student scored 100 on the second test. Good job. Student fell asleep on the third one. Got a 0. That's okay. And then student scored 100 on it again, and they learned the material, so they did pretty well. Now we could take the average of these by like how you normally would. We would add these all up, 100 plus 100 plus 0 plus 100, and then divide all of those by 4, and then we would get an average of 75, because that would be 300 divided by 4, 75. Now let's look at it a different way. A different way that we could look at it is, how many times did the student score 100? Well, out of 4 times, the student scored 100 3 times. So what we can do is, well, let's take 3 divided by 4, that's 0.75. So 75% of the time, the student scored 100. So this is 3 out of 4 times. 3/4 is still 0.75. The other score that they received was 0. So how many times did they score that? Well, they scored it 1 out of 4 times, so a quarter of the time. So that means that 25% of the time, or as a decimal 0.25, the student scored 0. So if we take this and we add these two up, 0.75 times 100 is 75. And then 0.25 times 0 is 0. And then the student's average, weighted average, was 75, which is the same thing as we got here, just a different method. But when we're taking a look at isotopes and average atomic mass, we're going to use this weighted average. And so we're going to go ahead and take a look at something else right now. Mass spectroscopy is how we figure out isotopic abundance between isotopes, between naturally occurring isotopes. So let's take a look. So over here we have a mass spectrometer. And in the mass spectrometer, what's going to happen is we're going to take the particular particles or the particular atom that we have. So in this case, it's magnesium, and it gets shot through this tube, and then it will eventually get collected. Along the way, we have 4 steps in this process. We have ionization, where we make this an ion. So what happens is you go from a magnesium atom with no charge to a magnesium ion with a +1 charge. Now, I know magnesium ions have +2, but they basically lose 1 electron in this process when it gets ionized. So if we take a look here, the electrons are knocked off from the sample particles, and you form mostly +1 ions, so +1 charge. So it's charged. And the reason why it's charged is because eventually it will get attracted over here towards the negative plates that we have over here. Remember, opposites attract. So the positive ions of the magnesium in this mixture of isotopes will get shot through the tube, and it'll get attracted towards the negative side. And so what happens is then in the mass spectrometer, we have an acceleration of the ions to speed them up. And so they go through charged plates, and then they travel at high speeds. And what happens is then after acceleration, then they get deflected. And when they get deflected, the ions are attracted to the negative side of the electromagnetic field. So here's the negative side and here's the positive side. So they get attracted to the negative, so they get bent. And they get separated based on their mass and their charge. And eventually they get detected at the bottom, and then the computer will read it out. And so they'll collide with the metal plate, and then the electrons are transferred from the metal to the ion, and then there's a current, and then that's how you get the signal in the computer. So if we're taking a look here, the atom will go through, it'll start here, and it'll get ionized, and then it'll become charged over here, and then as it goes through, it gets accelerated, and it increases in kinetic energy, and then some of them will make their way all the way down to the detection plate, and then you get the readout in the computer. And so that's what we have going on here. Now, 10 years ago, almost 10 years ago, I did a couple of summer internships at UC Berkeley with the mass spec and gas chromatography facility. And this was me using a mass spectrometer and preparing the samples for the machine to get ready to read. And so basically, it did all the stuff inside. It ionized it, and then it basically outputted the information to a computer. Now, what we also want to take a look, then you would see here, is you would see this particular reading for a mass spectrum of chlorine. And so chlorine has two isotopes, and like it says here, it has approximately 75.53% of chlorine-35 with this exact AMU, this exact mass, 34.97. And then the other percentage is 24.47%, which is exhibited by this smaller peak. And if you take a look, if you go straight across, you can actually take a look here, and that's about 24% or 25%. And you go over here, and this is about 75%. So now, just a couple of things to point out about here. Since the relative abundance of chlorine-35 is much greater, then normally in real life, if we took the average between 35 and 37, we would get 36. But since the isotope chlorine-35 is more abundant, then what's going to happen is the average atomic mass of chlorine is going to be closer to 35 than 37, because if you take a look here, the relative abundance of chlorine-35 isotope is much greater than 37. So there's a greater weighting of isotopes here, and so it'll count more towards the average atomic mass. That's why the average atomic mass is closer to 35 than 37 for chlorine, and that should be just Cl. All right, so there was that was that. All right, so let's go on to an example, and we'll take the example with boron. So let's take a look at boron. Boron has two naturally occurring isotopes, boron-10 and boron-11. So similar to what we had taken a look at just recently with the chlorine, let's figure out what percent or what relative abundance of naturally occurring isotopes would be boron-10 and which ones would be boron-11. Now, let's take a look. We don't know the numbers, but we do know that, say, for example, if 30% of all boron isotopes are boron-10, what percent, if there's only two of them, what percent would make sense would be boron-11? Well, it should make sense that it would be 70%, because 30 plus 70, if there's only two isotopes, which in some cases there are, some cases there's more than two isotopes, like maybe there's 3, 4, or 5, then these should add up to 100%. So if I'm expressing this as a decimal, this could be like 0.3 or 0.30, and this could be 0.70. Now, if I made this 0.30 equal to x, how would the 0.70 relate to the x, or the 0.3? Well, if we take a look here, if we took 1 minus 0.30, or 1 minus x, that would equal 0.70. So then that means that, like we did in the problem beforehand, let's take a look at the beginning with our test scores. So 30% of the time, or x% of the time, we'd have boron-10. So we're going to take x times the mass, which was 10. And we're not given specific ones, so we'll just use these numbers. But if you're given specific masses, then please use those. So now we're going to take the percent here for the boron 11, which is 1 minus x as a decimal, and we're going to multiply that times 11. And all of that should equal, and if we looked on the periodic table, I looked it up, boron's average atomic mass is 10.81 atomic mass units, AMU. So I'm going to take that 10.81, and so make this all equal to 10.81. And so that should allow me to solve for x because there's only one variable here. So if I expand this, this is 10x plus 11 minus 11x equals 10.81. And you do a little rearranging, you get negative x equals negative 0.19. And then so x would equal 0.19. So in this case, it's not really 0.30, but I just used it to illustrate. So the real number is x was 0.19 because we solved that for that here. So that means that 19% of all boron isotopes that are naturally occurring are boron 10. And so then that means that 1 minus 0.19, which is 0.81, that means 81% of all boron isotopes are boron 11. And that should make sense because if we would take a look between 10 and 11 for the mass, the average atomic mass is closer to 11. And so we should have a greater percentage of boron 11. Now we could do the reverse just to show, and I'm going to set that up right now. So we're going to go reverse, and we're going to find the average atomic mass based on, now we have the relative abundances, or the percent abundance. So we'll take 0.19, and we'll multiply that times 10, which is the mass. And then we'll take 0.81, and we'll multiply that times 11. And then that's going to equal something. Now when we do the math, we end up with 1.9 plus 8.91, and then that gets us 10.81 AMU, which is the average atomic mass of boron. And so we showed both ways how you can get from two isotopes, how you can get the relative abundances, and then also you can go the other way and get the average atomic mass.